Hi everyone. In this tutorial, I'm going to be going over how to run PySCF through our new pyRUQT calculator. So the first thing I'm going to show you is how to access the code to run this. So you're going to enter any of your RDMs, and now we're going to go into the directory of work and examples, and then go into the LI wire example. And the code that we're looking for is the liwire_pyruqt.py. So this is the script that we're going to be working with, and I highly encourage you to copy and paste this into a document just to make it easier for you to edit it. And just as a reminder, that's located in the work directory in examples liwire example, and it is specifically the one that is liwire_pyruqt.py. So now that we have our script, I'm going to go over what each part means and things that you might need to change within your script. So just to start off, I'm just going to go line by line. The first thing that we're doing is importing pyRUQT, which is the calculator that is running the calculation and taking all of these settings and importing them into the calculator. RUQT is the same thing. It's just not a Python script, so these two work together to produce both the model.dat and the transmission and everything that we need to run our calculations. Thankfully, Dr. Hoy, when he was making this, he did add a lot of great comments in here, so you can kind of follow along through that. But the next ones are calculations that you need for any type of calculation, and this is going to change for all of your calculations, right? So the method can either be DFT, which is density functional theory, or MCPDFT, which is multi-configural pair density functional theory. What density functional theory is approximating the electron-electron interactions not through single body, double body, or three body interactions, but rather than just taking what we would often refer to as an electron cloud approach, where we're not necessarily calculating specific interactions, but more so just an average of the interactions of the electrons within a system. What MCPDFT is, it takes the same stuff with DFT, but it adds that to those multi-body interaction calculations, which are often a little bit more expensive computationally because they take a lot of matrices and it's a whole long calculation for the calculator to do, but they are oftentimes more accurate to the system. Moving on to the XYZ directory, this is the directory in which your XYZ file is in. We always recommend that you put your XYZ file in the directory which you are running your calculation. So that's why we have the period slash. What the period slash tells the computer is that it is in the directory in which the calculator is running in, or in which the script is located in as well. Next thing is the name of the XYZ file. And for mine, I named it benzene.xyz. So you just want to have the full name of the XYZ file. And you'll notice throughout this that I did highlight a few of these settings, and these are the settings that I personally have to change very often in my calculations. So these are ones that you also might change pretty often throughout your calculations. The next thing is the DFT functional, which a DFT functional is the mathematical expression used, or the function that is used to calculate the energies that will be calculated in DFT or MCPDFT. Our group commonly uses PBE, so that is usually what we kind of stick to in our calculations. There are a ton more out there, but PBE is the one that we usually stick to. The next thing is the basis set, which is the equation or the setup that the calculator will use to calculate the molecular orbitals in your system. For systems that have gold, we commonly use LANL2DZ, and for systems with aluminum or that is a biomolecule, we'll often use a different basis set. The next is the ECP, or effective core potential. If you are running a calculation with LANL2DZ, you will need to set your ECP to LANL2DZ. What the ECP basically does is it takes a lot of the computational effort away from what we call core electrons and focuses more of what we can call the computational effort on the valence electrons, which for a large metal like gold can greatly help with the efficiency of the calculations, as instead of calculating the many electrons that gold has, it focuses on the valence electrons, which are commonly known to be the most impactful in these calculations. The next thing is the out file, which is just the name in which you want your out file to be. We always recommend that you name it the same thing as your XYZ and your .py file. This just makes things really simple, so we always name it the same thing. The next section of the script is for the semi-infinite calculator, which is the calculator where we're using large electrodes with multiple repeating units for something like a supercell calculation. So in this section, if you are running a wideband limit calculation, you can just ignore this part. But if you are running a semi-infinite, which we will be running in the next tutorial where I show myself running this script, we are going to play around with this a little bit. xmlprog is the program in which the calculation is going to be run through. In our group, we run our calculations either through PySCF, which is Python Self-Consistent Field, or Mulcast. And Mulcast is an open source calculator, which we do use both. But in this example, we're going to focus on the PySCF. Now, the number of electrode atoms is really important here, and we want to get this number right because this is the number that it will use to base the transmission calculation on. What we used to have to do before was give the script the number of orbitals, which was a fairly tedious process. We now have developed a way in which we don't have to do that. So we simply just have to put the number of electrode atoms that are present, and it takes that plus the basis set and is able to calculate the number of orbitals for you. So here's just an example system to give you an idea of what this number would look like. So usually in a supercell calculation, we're working with 3 layers. So let's say this is layer 1, this is layer 2, and this is layer 3. It's likely going to look different, but I just have this simple molecule to show you in a really easy light. We have 3 layers here, but using the supercell calculation, we want to just do 2 layers of the electrode. So we're going to count the number of atoms that is in just 2 layers. So we have 1, 2, 3, 4, 5, 6, 7, 8. It might be a little bit more difficult when you have a bigger electrode, but in that case, you could go into the XYZ file and count it that way. So for that example, we would set num_elect atom equal to 8. The rest of the settings here are pretty standard. For instance, minimum transmission energy would be -2 to 2, and that's the amount of electron volts that it's going to scan to and from. The delta energy, min bias, max bias, delta bias, temperature, full line, align with atom, and DOS calc, which is density of state. These are all things that you might change, but these are pretty standard, and at least for my personal project and a few of the other projects that we are currently working on, we do not change these. Again, in future projects and in different subgroups, these will be changed to analyze different properties of different molecular junctions or different sensors. So just keep in mind that although I am not changing these settings in my example, you might need to change them on your end. But unless you are told so, you likely don't have to. The next section in the script is the MCPDFT section, where changing these settings is only going to affect if you are using the multi-configural pair density functional theory. The first thing is MC-SCF type, and this is the complete active space configuration that you are using. So we tend to use CASCI, which is complete active space configuration interaction, and this uses predetermined orbitals. But you could also use CAS-SCF, which is complete active space self-consistent field, and this is where the orbitals are optimized through the calculator. So there's some pros and cons, and you might need to look into what is best for your system. The next thing is the SCF solver, which is the self-consistent field method that you are using in your calculation. In our group, we mainly stick to RKS, which is restricted cone-sham, or restricted Hartree-Fock, which is RHF. And what restricted cone-sham is it's using a density-based method, so similar to DFT, whereas restricted Hartree Fock focuses more on the wave functions and doing the individual calculations through that. The next thing is the active space, and the active space gives you two numbers, where you have here is the number of electrons that are being accounted for in the calculation, and then the second number here is the number of orbitals that are accounted for in the calculation. These numbers usually will be the same because we want to have the homoluma, where we have occupied orbitals and then we have unoccupied orbitals above those. We usually do 4 by 4, 8 by 8, 12 by 12 are our usual numbers. But again, this is something that is really based on your system. The smaller the active space, the quicker the calculation will run, but that also will play into the accuracy. And the larger active space will run a lot slower, but it will be slightly more accurate as it's using more computational effort to calculate more molecular orbitals. Now, the active orb or active orbital is only used when we are reordering. We're going to talk about that in a future video and how to reorder the active spaces, but you do not have to worry about that for now, but that is what that is used for. And with auto AS, this is the auto active space, which means that when you set this to false, the calculator does not automatically select active orbitals for you. So when we set this to true, the calculator does automatically select active orbitals for you. Verbosity is not super important here. It's actually just the amount of information that's stored in the .log file. So if you want more information, it's likely going to take longer to run, but we like to keep ours at around 5 since we feel as if that gives us enough information to see convergence issues and to look into the energies and the matrices that it's calculating, etc. Moving on to the next section, this one is very small, and this is the command used to generate orbital visualization. So if you're working in a project where you want to visualize the homoluma orbitals, you want to visualize the orbitals that the calculator is predicting, you would want to set this to true. I would say most often you want to set this to true because that will then generate the Molden file that you need for visualizing the orbitals, and it's very nice for checking to see different transmission trends, conductance trends, etc. But if you are just running a calculation where you don't need to see the orbital visualization and you are just trying to get something to converge, or you're just trying to get the energy, or you don't really need to know about how the orbitals look, you can set this to false. Now onto the final section. This is the most important section in my personal opinion, and this is the PySCF convergence settings. From my experience, these are the settings that you are going to be playing around with the most. A lot of testing and trying different things out, because PySCF does struggle to converge a lot, especially for larger systems. So this is where this becomes really important. So as you run the PySCF calculation, what it's trying to do is converge to a certain energy based on the different parameters and the molecule that you gave it. So it's running cycles, right? And as it's running these cycles, what you want to see is the difference in energy between the cycles to be extremely small, right? Because we want it to converge to a certain point. So the differences between the cycles should be small. This is often referred to as the delta E in your .log file. So in order to get the calculation to converge, we need to set the convergence tolerance to a point where it will converge, and it's also a low enough point to where we know our calculation will be accurate. I always like to set mine to somewhere in between 1 times 10 to the negative 5 to 1 times 10 to the negative 7. The smaller that the number is, or the larger that the exponent is in the times 10 to the whatever value, the more accurate your calculation is going to be, because you are decreasing that convergence tolerance. So it's going to be harder for the calculation to converge, but you're going to get a more accurate answer. So for this number, I would say you should probably try to stay in somewhere between -5 to -7 area. Again, this is something that as you run the calculation, you will see what is possible for your system and you can kind of go from there. Now, what max iter is, that is the maximum iterations. This is the number of cycles which your calculation will run, right? So we discussed that it's running cycles, but we need to give it a maximum number of cycles because if we don't, it possibly could run for forever and we don't want that to happen, right? So we always like to start with around 200, as this tends to give just enough to where if it's going to converge, it has a great chance to converge, but it's also not running on for forever and ever and ever. So this is a number that you can adjust as you need and as you see fit. For instance, I was running a calculation today where I wanted it to converge within 30 cycles, just so that I could see how the delta energies were looking in the first 30 cycles. You can always increase this or decrease this. We like to keep it right around 200. The next thing is the SCF algorithm or the SCF algo, and this describes to the calculator how it should converge. So this gives the calculator kind of an idea of how it should be handling the cycles and the iterations and how it should be focusing on converging. There's many different types of SCF algorithms, such as ADIIS, which is the one that we currently use for most of our calculations. There's EDIIS, there's CDIIS, and many, many more. I highly encourage you to look up the differences between these and even see what could work best for your system. And this is a really good tool because if you are struggling to get your calculation to converge, changing the SCF algorithm could help get you unstuck out of a convergence issue. The DIS start cycle is just as it sounds. It's the cycle in which the DIS or the SCF algorithm is going to start. So you might be wondering, why would we want to start it later? Why wouldn't we want to start it automatically if it's going to help the calculation? Well, the beginning iterations or cycles are really rough guesses. So when we start the DIS start cycle a little bit later, it allows it time to kind of stabilize, right? And the DIS start cycle, along with damping and level shift, are some really important values that you kind of want to be playing around with, and they will go hand in hand. So to move on to damping, this smooths out the initial iterations.
When running a calculation with damping, it's important to remember that damping is a number out of 1 because it's represented as a percent. So damping at 0.2 would be 20%. And you don't want to reach above 100%, as this will lead to more issues than aiding you.
So usually you want to start the DIS cycle a little bit later because you want to allow the damping to kind of take control and work on smoothing out those beginning guesses. So just to reiterate, we have the DIS start cycle set a little bit later so that we can then allow the rough guesses, the rough beginning guesses, time to stabilize, and we can aid that stabilization through damping, which smooths out the initial iterations. Now moving on to level shift, this shifts the unoccupied orbitals to a higher energy. This aids in the stabilization and convergence, and it also ensures that electrons don't enter the virtual state or the unoccupied orbitals, right? Because we don't want that to necessarily happen in our calculation. We want them to stay in the HOMO, the highest occupied molecular orbitals, throughout the calculation. So these settings that I've just discussed are the ones that you probably will be playing around with the most, and they will help with your convergence issues because of all of the different things that they affect in the calculation. Now moving on to the SCF guess. This is the initial guess that you can give to your calculator to aid in calculating these energies and orbitals. Some examples are min-AO, or minimum atomic orbital, atom, check file, etc. There's many online. This is another thing similar to the SCF algorithm where you can do some research and kind of figure out what would work best for your system. I would like to specify that check file, CHKFILE, is a really valuable tool as you can start your SCF guess from a previous calculation, right? So let's say I ran a calculation and it was very close to convergence, but it didn't quite converge yet. I can set the SCF guess to that past check file, and it will use that in the next calculation as its beginning guess, so that it has a already almost converged start, and it will likely converge once you add in that check file and give it a nice and easy guess for it. Lastly, we have fractional occupation. Now, this can also be useful for convergence issues, as what fractional occupation does, as instead of 0, 1, or 2 electrons occupying an orbital, you can now have 0.5 of an electron, 1.5 of an electron occupy an orbital. This tends to be good for converging with metals because metals, as we know, are kind of act as a sea of electrons, where they're constantly flowing through and moving and jumping around different energy levels. But this is another thing that, again, you'll have to look at your system and look at your convergences and see how they're looking and kind of go from there. Now, finally, we are moving on to the last part of the calculation, and that is the things that actually call all of these variables and get these to converge. So there are two here that we have listed. You only need one of them. So here we have hashtags, which is what we call commenting out in coding, where if you have a line of code and you put a hashtag in front of it, that code is not read by the computer. So it will not be read by the computer, right? So if I were to take this one here and put a hashtag, that means that the computer will not read any of this information here. So what this first one is this is the PySCF subroutine. So as you can kind of see here, it's asking for the out file, the XYZ. We can kind of go through. It's asking for vibrosity, display orbitals, DISS start cycle, etc. So those are the things that we talked about, right? So this calculation here will only provide you with the mol.l.dat, and it will not run the transmission calculations, right? Because it's not asking for any type of electron program. It's not asking for anything of that nature, right? So if you're just trying to generate a mol.l.dat file, or you are just trying to generate a mol.den file to analyze the orbitals, you would run this calculation. But if you would like to combine the two and run both a mol.l.dat and generate a mol.den and generate your transmission calculations, you will do this here, right? So this is where it's going to ask you if you want to use the supercell, if you want to use PySCF. Let's say that you change this to wideband limit, you would add in that this would be wideband limit calculation, etc., right? So this whole big chunk of code is telling the computer, okay, we're going to run a pyRUQT and we're going to run a transmission. This is the type of transmission that we're going to run, and we are also going to generate the mol.dat using all of these settings, right? And just as a reminder, you only need one of these two, right? So let's say I did want to run a calculation where I just generate a mol.dat. What I'm going to do is I'm going to remove this hashtag and put a hashtag here so that this whole thing is no longer running and this one is running. And let's say we want it the opposite, where I do want to run the transmission. I'm going to put that hashtag back here and remove this one. Okay, so that's it for this video. I hope that this was helpful in explaining what all of these different keywords and variables mean in the PySCF calculator. In the next video, I'm going to go a little bit more into depth about the convergence issues and how to solve them, and also show you how to actually run one of these calculations and analyze the results. Thank you all for watching, and I hope this helped.